Did you know that the Pythagoreans supposedly killed an individual for proving that the square root of 2 is irrational? Did you know that real analysis is one of the most fundamental subjects in mathematics, yet involves some of the most advanced mathematical entities ever involved in mathematics itself? Well, in this video, we're going to be talking about real analysis, and this is the second part on our series on real analysis. Hi everyone, welcome back to my channel, and today I'm going to be talking about real analysis. In this video, we're going to be talking about how number systems form number fields after following a certain set of axioms. Near the end of this video, we're going to be talking about how to prove that the square root of 2 is irrational, as this is an important proof in mathematics itself. In our previous video on real analysis, we talked about what real analysis actually is, and we talked about the fundamentals of real analysis itself, namely axioms and sets. So if you want to learn more about axioms, sets, and what real analysis actually is, please visit that video on real analysis. Okay, so let's begin by listing the number systems which we're going to be talking about in real analysis. So first, we have the natural numbers, then we have the whole numbers, then we have the integers. After that, we have the rational numbers, and last but not least, we have the real numbers. Now, these are the 5 number systems which we're going to be talking about today. Now, there are more number systems. For example, we can consider the complex number system. But as the name suggests, real analysis only studies real numbers and what can be built upon them. Now, there's a subject called complex analysis, which is built up on real analysis and involves complex and imaginary numbers. Okay. So it's important to realize that the natural numbers, whole numbers, integers, and rational numbers are all subsets of the real numbers. So let's talk about each of these number systems and then proceed forward. So what are the natural numbers? The natural numbers are essentially called the counting numbers. In other words, they contain positive integer values starting from 1. But we can only define that if we know the integers. So therefore, we can just define the natural numbers as essentially a set starting from 1 and then going to 2, 3, 4, 5, 6, etc. And these are essentially the counting numbers. So these are the natural numbers. Now notice that all the number systems which we're going to be talking about right now are infinite number systems, or infinite sets, more specifically. In other words, they have an infinite number of elements. Okay, so that's the natural number system. Now the whole number system doesn't draw a much broader conclusion, which we can phrase it, from the natural numbers. The whole numbers just essentially as 0 to the natural numbers. So if you have 1, 2, 3, 4, 5, 6, 7, 8, etc., then you just add 0, 1, 2, 3, 4, 5, 6, 7, 8, etc., then you get the whole numbers. So that's what the whole numbers actually are. Now we have the integers. Now the integers are some of the most important numbers in mathematics, especially in number theory, a subject that studies numbers. Now the integers, in fact, over here, as one can see, have the negative numbers. So they're essentially the whole numbers because they contain 0 and 1, 2, 3, 4, 5, 6, 7, 8, etc. But they also consider their negative counterparts. So they have negative 1, 0, 1, etc. So we can just represent it by this. So it goes infinitely in the negative direction and infinitely that way in the positive direction and contains 0. So that's the integers. Now we have the rational numbers. These are some of the most important numbers in mathematics because, as we'll talk about later, they form a field. Now, the rational numbers can just be stated as any number that can be represented as P over Q, where Q does not equal 0. Now, it's important to realize that 0 does exist in the rational numbers, but Q cannot be 0 because then that would become undefined. So 0 can be in the numerator, on the numerator, but it can't be in the denominator. Okay. Lastly, we have the real numbers, which primarily contain irrational numbers, rational numbers, so they contain irrational numbers, they contain rational numbers, they contain integers, whole numbers, natural numbers, and etc. So they contain pretty much all the numbers which we can think of that do not have any relation to the complex numbers. Now, we'll talk about the completeness axiom and how this relates to the real numbers later, but in this video, we're just going to be talking about how they relate to the fields and the field axioms and how the rational numbers and real numbers only form a field. Okay, now that we've talked about the basic number systems in real analysis, let's continue to talk about the properties of rational numbers. So what are the properties of rational numbers? Now, over here listed, we have two properties that we must consider. We have closed and nested. So in other words, the rational numbers is closed in addition, subtraction, multiplication, and division, and it is nested. So what does this mean? Closed means that if we take any two numbers in the rational number system, so let's say we take 5 and 4, and we do addition, subtraction, multiplication, and division to these numbers. So let's write this out. So we have 5 times 4, 5 divided by 4, 5 minus 4, and 5 plus 4. What closed means is that all of these are essentially in the rational number system. So if we take any two numbers in the rational number system and we do any one of these operations, addition, subtraction, multiplication, or division, then we will always get another number that's in the rational number system. Now, this does not satisfy some of the properties in all of these. For example, let's consider the integers. If we consider the integers, we can see that they don't have 1 divided by 5, or 1/5. So they fail. Now, it's important to realize that the whole numbers is a subset of the integers, and the natural numbers is a subset of the whole numbers. And so the natural numbers is also a subset of the integers, which means that if the integers aren't closed, that means under division, which means that the whole numbers aren't closed under division and the natural numbers aren't closed under division. More specifically, the integers, yes, indeed, they have subtraction, but the whole numbers and natural numbers cannot. Because if we have, let's just say, 2 subtracted by 4, we get -2. And that's not in the whole numbers or the natural numbers. So the whole numbers and natural numbers aren't closed under division and aren't closed under subtraction. Now they are closed under multiplication and addition, because multiplication of two positive values always results in a positive value, and moreover addition of two positive values always results in a positive value. So if we think about that, then yes indeed, they do satisfy to being closed under addition and multiplication, but not division and subtraction. So natural and whole numbers are only closed under addition and multiplication, integers, addition, multiplication, and subtraction, rational numbers, addition, multiplication, subtraction, and division, and real numbers, addition, multiplication, subtraction, and division. In other words, natural numbers, just recall again, natural numbers and whole numbers, they are only closed under addition and multiplication, integers, addition, multiplication, and subtraction, rationals and real numbers, addition, multiplication, subtraction, and division. Okay. Now that we've talked about one of the properties of rational numbers, which is essentially being closed, let's talk about being nested. Now, nested, as the name suggests, just means that if we have any two numbers from the rational number system, let's say we have 4, and let's say we have 5. Now, if we have 4 and 5, what essentially the rational number states, or what the property of nestedness states, is that there is always a number between any two rational numbers. And if we think about this, this is true. We can have 4/5. Well, not 4/5. We can have, let's say, 4 and 1/5, 4 and 2/5, 4 and 2/5, and yes, indeed, these numbers are between 4 and 5. But if we consider the integers, whole numbers, natural and natural numbers, let's say we have 1 and 2. In naturals, wholes, and integers, there is not any number inside of these two numbers. So if we think about it, there isn't a number between these two numbers in the integers, whole numbers, or natural numbers. So the property of rationals and real numbers is that they're nested. Now that we've talked about that, let's move on to talk about what a number field actually is. So what is a number field? We've been talking about the notion of a number field since the beginning of this video, but we haven't properly defined it. A number field is essentially just a set. Now the set can't be empty, it has to have some elements, and this set essentially has two binary operations, addition and multiplication. If it does, then it's a field, but it has to satisfy these 5 axioms over here. Now, if it satisfies these 5 axioms, then of course it's a field. If it doesn't, then there's a problem. Okay. So let's check each of these to see if they're a field. Natural numbers, commutative law, which is a plus b equals to c, and a times b, well, if the commutative law states that a plus b is equal to b plus a, and a times b is equal to b times a. Distributive law is a parentheses b plus c is equal to ab plus bc, well, not bc, ab plus ac. Associative law states that a plus parentheses b plus c is equivalent to parentheses a plus b and parentheses plus c. Identity law states that if we have, let's say, a times 1, this must equal to a, and a plus 0 is equal to a. And last but not least, inverse law states that if we have a, then a times, a minus a equals to 0, and a times 1 over a is equal to 1. So that's the inverse law, identity law, associative law, distributive law, and commutative law. Now, it's important to realize that the commutative law, distributive law, associative law, identity law, and inverse law, they're all very important. So let's see if the natural numbers satisfy this. Commutative law, yes they do. Distributive law, yes they do. Associative law, yes they do. Identity law, they don't have a 0. Therefore, the natural numbers are out. Next, we have the whole numbers. The whole numbers, commutative law, yes. Distributive law, yes. Associative law, yes. Identity law, yes. Inverse law, they don't have negative numbers, therefore, nope. Integers. Commutative law, no. Distributive law, no. Associative law, no. Identity law, yes. Well, I mean, commutative law, yes. Distributive law, yes. Associative law, yes. Identity law, yes. Inverse law, they don't have fractions. So therefore, integers are canceled out. After that, we have the rational numbers. The rational numbers. Commutative law, yes. Distributive law, yes. Associative law, yes. Identity law, yes. And inverse law, yes. They satisfy, and since the rational numbers are a subset of the real numbers, they are also satisfy. And in general, if you do check these axioms, they do satisfy. So these are the number fields. Just to recap, the commutative law, distributive law, and associative law are, and identity law are satisfied for the integers. Okay. Now that we've talked about that, let's move on to the most important part of the video, which is to prove that the square root of 2 is irrational. Okay. Now, this proof is a pretty simple proof, but we have to define some things because this is a proof by contradiction. In other words, we define something, or we presumably assume something at the beginning, and then we find that there's a contradiction. And that's essentially the method of proof by contradiction, which is pretty self-explanatory. So the proof for the square root of 2 is irrational. So we're going to complete the proof. So let's state that P over Q is equal to the square root of 2, where we're going to be saying that P and Q are in simplest representation. In other words, I mean they can't be simplified. Okay, so remember that Q can't be 0 because we're dealing with rational numbers. The definition of irrational number is pretty much not rational. Okay, so let's first do some algebraic manipulations. Let's multiply by Q. So we have P equals square root of 2 times Q. Now, let's essentially square both sides. Therefore, we have P squared equals to 2Q squared. Now let's divide by 2. So we have P squared divided by 2 is equal to Q squared. Now here's an important part. If we see P squared is divided by 2, then we can deduce that P also divides by 2. If we think about it, 4 times 4 is 16. If we have 16 divided by 2, of course, there's going to be a number, there's going to be a number that works. And there's going to be a specific number, which multiplied by 2 is equal to 16. But then again, we can see that 4 divided by 2 also is a whole number, which means that we get, let's just say, 2 in this case. So therefore, we can see that if P is even, and P squared is even, so if P squared is even, then P must be even as well. So P divides 2. Well, P over 2 exists. That's what we're just going to be boxing right now. Now, it's important to realize that just because we've stated that P divided by 2 exists, which means P is divisible by 2, doesn't mean that we've come to a contradiction. Because we stated that P over Q is in simplest terms. Because just because P is divisible by 2, doesn't mean Q has to be divisible by 2 as well. Okay, so let's continue. Now, we're going to make a substitution. We're going to state that P is equal to 2K. Now this is valid because we know that we know that 2 divides P, which means that 2 times K is equal to P. So what we do is we just plug this in. Now let's first multiply by the 2 on both sides before we do that. So we have P squared equals to 2Q squared. Plugging in 2K, we have 4K squared equals to 2K squared. Dividing by 2, we have 2K squared is equal to Q squared. Divided by 2 again, we have Q squared over 2 is equal to K squared. Now, right now we're just saying that Q squared, 2 divides Q squared, which means that 2 divides Q. And since we stated that, we see that 2 also divides P, and 2 also divides 2 now. So we're going to state that Q over 2 exists. We're going to box that. So therefore, we stated that they're in the simplest terms. They don't have any common factors. But if 2 divides both of them, that's a contradiction to our original assumption. And therefore, the proof is over. Now usually in proofs, they draw a box at the end and color it in just to say that it's the end. So that's a proof that the square root of 2 is irrational. It's a proof by contradiction, and it's a very important method in mathematics. Now that we've talked about that, we can make this video to an end. In this video, we talked about number systems, and we showed how the rational numbers and the real numbers are the only 2 number systems that form a number field. We talked about the axioms that form a number field, which are the 5 axioms. commutative law, distributive law, associative law, identity law, and inverse law. Lastly, we talked about how to prove that the square root of 2 is irrational, which is a proof by contradiction and one of the most important proofs in mathematics. Now that we've talked about that, we can make this video to an end. If you like this video and if you like this channel, please subscribe to learn more. Thank you.